Hello, this is our first in a set of 4 recordings on inference for counts and proportions. Previously, in our discussion of statistical inference, we've focused on continuous measurements, that is, things that are measured on a continuous scale, like weight, length, strength, temperature, and so forth. But sometimes we have to deal with what is sometimes called categorical data. Here, the variables of interest are not on a continuous scale, but they're on a scale of categories. We say categorical data. Jump sometimes calls it nominal data. So instead of taking continuous measurements, what we actually look at are the frequencies with which different categories or levels appear. A simple example would be to open a bag of M&Ms. The variable of interest is color, and we'd simply count the frequency with which each color showed up in the bag. So in this first video, we're going to talk about inference for a single proportion. So there's a single categorical variable of interest, and we want to draw some conclusions about it. And this is the notes on inference for counts and proportions. Okay. And again, there are many scenarios in which this type of data or categorical data occurs. One thing I will tell you in terms of continuous improvement projects, categorical data is information poor. There's not a lot of content to it, unlike continuous measurements. Therefore, you need far more data to try to draw conclusions. And in fact, if at all possible, you are always better off using continuous measurements and abandoning categorical measurements or scales if at all possible. Believe me, it makes a very big difference in your ability to understand some process or system and to make improvements. So we're going to begin by talking about a confidence interval for a proportion. And in this case, a proportion refers to the proportion of successes or events that would occur over time for some nominal variable. A good example would be, what is the true proportion of voters who will vote for Donald Trump or Hillary Clinton or some other candidates? And we can go out, we get a sample, we measure the sample proportions, but those are only estimates. They don't tell us what the true proportion might be, and in fact, the true proportion is actually unknowable. So one of the ways we try to draw inferences from the samples about what the true proportion might be is the use of what is called a confidence interval. And again, this is a case for a single proportion, and we'll look at a case where in each trial there could be a success or failure. So let's take a look at the data called orders 1. In this data, 50 records have been pulled for orders that were placed, and they have been checked for accuracy. So in the data orders 1, we have listed all 50 records and whether or not the order was correct. Well, in reality, this is actually a waste of time, since there are only two values that are available, yes or no. Why would we list the table out with every single one of the records when, in fact, as I'll show you, we could do them in tabular form? So I'm going to go over to Jump and explain the analysis, how we generate a confidence interval and do a hypothesis test for proportions. Okay, so go to Jump, and this is the orders 2 data, which is tabulated. It really doesn't matter which way you do it. The other approach would be to list out all 50 observations. So in this tabulated form, notice there is a column that gives us the count. So the variable of interest is correct with a question mark. It has only 2 levels. It can have more. Okay, but we're going to just stick with the 2-level case. Jump really doesn't care, it'll just adapt to whatever you tell it. And there are 42 yeses and 8 nos. So again, I want to look at the distribution of correct. So I go to the Analyze menu, select Fit Y by X. I'm sorry, that was incorrect. I meant to say select distribution. So correct is Y, the nominal variable of interest. But we also have to tell Jump where the counts for each category are stored. So put count in the frequency box. Excuse me. So this is the report for a nominal variable. So 84% of the responses are yes, 16% are no. But again, these are sample estimates. This is actually a small sample of only 50. So to do some inference, I'm going to click on the report menu to the left of correct, and I'm going to select confidence interval, and we'll do a 95%. So what Jump is giving you are 95% confidence intervals for what the true proportion of no's or yeses might be. And for no's, it says somewhere between 8% and 29%. You say, well, that's a wide interval. Yes, it is, but we have a very small data set for nominal data. So our inference is that for this process of order placement, the actual error rate is somewhere between 8% and 29%, and that is the best I can do. I also want to point out there is an approach briefly talked about in the notes for confidence intervals based upon the normal distribution. Jump uses a different approach, which is known to be better, called the score confidence intervals. Again, it is beyond our scope to delve into the mathematics, but they are given to you briefly in Jump Help, and it's a more complicated formula. I'll just leave it at it is known to have better properties in terms of forming confidence intervals. Well, that's the primary form of inference for proportions, confidence intervals. However, we can actually do hypothesis tests, so click on the report menu to the left of correct, select test probabilities, and there are different options. I'm going to use the two-sided, it does what's called a two-sided chi-squared test, and then it does, if you want to do the one-sided case, it will actually use what are called exact binomial tests, or p-tests. Jump does not use the normal approximations that can be found in textbooks because in small samples they're known to have poor properties. So I'm only going to do the two-sample case, and I'm going to propose, suppose the manager for order entry is convinced that the error rate is no greater than 5%. By the way, you don't have to fill in the other category here. Excuse me. So I'm going to go ahead and do the test. And Jump does a couple of tests. I'll talk a little more about them, but what's called the Pearson test was invented actually well over 100 years ago. It's also known as the chi-squared test of independence. This is a test we'll use. There's another version that's more difficult to explain. It's more theoretical, called the likelihood ratio. Many statisticians prefer it. However, I find in general Pearson's test is straightforward, is commonly used, and easy to understand. So given we have a very small p-value no matter which test we use, we would reject the null hypothesis and say whatever the error rate is, it is not 5%. And in point of fact, if we look at our confidence interval, we can see 5% does not fall within it. Therefore, we would go ahead and reject the hypothesis. Okay. So that is the basic idea of inference for proportions. Now, I wanted to show you something else, and this is germane to the point I made that for doing inference on proportions, 50 is actually a very small sample size. And it turns out, if we go to jump help and we go to the sample data, okay, you'll notice it in the sample data window it says teaching scripts, and then it says calculators. So I'm going to open calculators. And what it does, sample size for confidence intervals. So I'm going to click on it. Okay. And I want to do a sample size for a proportion. What I'm going to do is, if I'm going to collect data and I want to know the true proportion with some level of precision, then in advance I need to know what the sample size is. Okay. So jump says, what is the confidence level? Well, I want 0.95. That's standard. Expected proportion. If you have no idea what this is, put in 0.5, and generally we don't. 0.5 is conservative in that it gives you the largest possible sample size, and let's suppose I'd like to know the true proportion within 3%, or 0.003. Okay. It tells me that I need about 1,068 observations. Okay. Notice our sample had only 50 and the confidence interval was very wide, very imprecise. Now, why this may interest you, these sample size calculations are done in figuring out samples sizes that are needed for political polling. So when you see a political poll given, they'll often tell you the number of people in the survey is in the range of 1,000, and the reason they do that, that gives them a margin of error of plus or minus 3%. Okay, so if we have a little over 1,000 respondents, then within 3 percentage points we will know what the true percentage is, or the true proportion. So that's why in these polls you often see 1,000. Well, what if I wanted to know within 1%? Notice almost 10,000 respondents. That's why in political polls you will rarely see anything beyond a margin of error of plus or minus 3. Meaning we only know what the true proportion is within plus or minus 3%. Polls where they do 1% are very large, very expensive, can easily cost $1 million to do. So if you're going to do a study and you're using a nominal or categorical variable, it's a good idea in advance to understand the sample sizes that are needed to draw meaningful conclusions.